Okay, so hi, welcome to this next video in linear programming. So this is the beginning of the topic of geometry in linear programming. So typically our formulation is this, where we have max E transpose x equals b, x is non-negative. And then A is usually assumed to be m rows, n columns, and it's full row rank. All the rows are linearly independent. We're going to be dropping this this format. This is standard equality form, and we're going to be going to a different format for the perspective of geometry. So we'll get there in just a second. But the point I first want to make is that if you consider a point x in Rn, which satisfies all of the constraints, right? So ax equals b and x is non-negative, then so that would be a feasible solution to the linear program. We're going to view those as points in Rn. So geometrically, these are points in n-dimensional space. That's pretty obvious, of course. You were probably already thinking that, but now we're going to start asking the question of what does the set of all the solutions look like? So I look at the space Rn and I look at where all the points x satisfying these constraints are. So, like, are they just randomly scattered about in space, or is there more structure to them? And so the answer to the first thing, are they scattered about in space? It's no. It's almost the exact opposite of that. They're very, very highly structured. So we'll see what that is in just a moment. So in order to analyze things from a geometric perspective, we're going to rewrite linear programs to make it more amenable to geometric techniques. And so if your linear program is written in standard equality form, maybe it's not, but if it is, then the way you can convert to this to a new format, where the new format is going to be, we have a whole bunch of less than or equal to constraints. So every constraint will be a less than or equal to now. And so if you are in standard equality form, the way you can go to this new form is, if I first consider the matrix equality constraints, so look at a row of the matrix A corresponds to a constraint. So if I have a particular constraint, then and it's equal to, then what you can do is you can just write that as a less than or equal to and a greater than or equal to constraint. It's both of those simultaneously. And then so there's a less than or equal to, so you're good there. And then the greater than or equal to, all you have to do to flip it to be less than or equal to is just multiply both sides by -1, like I've done in this purple update here. And so these two red asterisked constraints are the ones we want. So they're equivalent to this original constraint, but they're both less than or equal to. So that's what we want. And for the variable non-negativity constraints for each individual variable xj, it's greater than or equal to 0, so just multiply by -1, and now you have minus xj is less than or equal to 0. And so there you go. All the constraints are now of this less than or equal to form, which will be more helpful for us. And since every single linear program could be written in standard equality form, then we can conclude that all linear programs can also be written in this form, C transpose x, such that a bar x is less than or equal to b bar for some choices of a bar and b bar. Since it might not be the case that your linear program originally comes in standard equality form. You might have had to do some work if you want to convert it to that in the first place. But maybe it's of a different form. But if it is of that form, and we could, in principle, put it in that form every time, then we can do this conversion. But the takeaway message is that if I'm just considering the linear programs that can be written like this as all less than or equal to constraints, that's actually all linear programs. I'm not excluding any. If I want to have this format, every linear program can have this format. And I'm just going to drop the a bar and b bar from the notation. I'm just going to say max C transpose x is such that ax less than or equal to b, just because so it's just a new a and b. I'm not referring to the original matrix a and b from the standard equality form. We're just it's just new notation, and just so we don't have to keep writing bars over everything, because we're not going to be referring back to the standard equality form. So, okay, and what's the advantage of writing it like this? Well, it's easier to analyze geometrically. So let's see why with an example. So, so here's an example. It's max, I don't care actually what the objective function is, just fill in whatever you want, it doesn't matter. What we care about is the constraints. We're looking at the solution set, the feasible solutions. So this is in two-dimensional space. We have two components, x1 and x2. So we can draw this on the plane here in R2. And so if you look at this set of constraints here, I have, for instance, this row corresponds to a constraint. And so I have x1 plus x2 is less than or equal to 3. And so over here, that would correspond to this blue line that's kind of going diagonally downwards like this. And so that's the line x1 plus x2 equals 3. And then for less than or equal to, I'm just taking everything below it, so to the left, kind of. And then similarly, for all of these constraints, there's an associated a line here representing the equality constraint, and then for less than or equal to, you're just considering things, above or below that line. I say above or below because you can't actually assume it's below, because for instance, this one is saying minus x1 is less than or equal to 0, or in other words, x1 is greater than or equal to 0. And so that would correspond to this vertical line here, and then we're to the right of that. But anyways, we're always just on one side of the lines here. And so the rows of the matrix correspond to lines, and then the solutions live on one side of those lines. And so that purple set is the intersection of all of those constraints. So it's not just that it's living to the left, below this diagonal line, because there's lots of points that live to the left of this diagonal line that are not solutions, but it also has to live above this line, to the right of this line, below this line, and to the left of that line. And so it has to satisfy all those things. And so when it satisfies all those constraints, you get that purple set there, and that's the feasible region. So all the points in space are packed into this shape here, and we call that a polyhedron. So we'll define what a polyhedron is in a moment. But first, let's just analyze this a bit. So look at one particular constraint. So for instance, that diagonal downward line. If we zoom in on that, so I've highlighted it here, so let's zoom in on it. What you're seeing is that we have that line, and then that line splits all of two-dimensional space, all of R2, into two sides. Side on the right of it and side on the left of it. That's we just call those half spaces. So there's a half space to the right and a half space to the left, split by this line. And so all the solutions to the linear program are going to live to the left here. Again, there's things that live to the left that are not solutions, but if it's going to be a solution, it is going to be to the left here. And that's true not just for this constraint, but for all constraints. For every single constraint, there's a line, and then the set of solutions will live either above or below that line. And each line splits space into two half spaces: the bad half space where the solutions don't live, and the good half space where the solutions do live. Okay, and so all the feasible points live in one half space and not the other for all constraints. So I just do this zooming in of for all these constraints, and that gives me and I look at the good half space according to each line that splits space into two halves, and then the good side, I take the good side according to each of those lines and intersect all those half spaces, and that gives me this purple set here, this polyhedron. And so yeah, so therefore we can conclude that this purple set, this polyhedron, is equal to the intersection of half spaces. It's in particular all the good half spaces. It's the intersection of the good half spaces. And so that's what a solution set looks like. It's always the intersection of the good half spaces. But in general, when you're asking what does the set of solutions to my linear program look like in space, well, it looks something like this, being the intersection of half spaces. Okay, and so now let's give a definition for what a polyhedron is. A polyhedron, that purple set that we drew, is a polyhedron, by the way. So a polyhedron is a set P of the form. Well, it's points x and Rn that satisfy these constraints: ax less than or equal to b for some particular a and b, whatever they are. So if you know the a and b in advance, and if we have a linear program, then we do know what the a and the b are. That these are the constraints of the linear program. Then a polyhedron will be the set of solutions then that satisfy these constraints. So so this blue comment is saying that. So the feasible region of a linear program is a polyhedron. Because if you give me a linear program, I'll have constraints like this, and then the associated polyhedron will be this, the points in Rn that satisfy those, and that's a polyhedron by definition. And so we said, so it's kind of like there's three different things going on. It's the feasible region of an LP, there's the term polyhedron, and then there's this notion of intersection of half spaces, and they're all the same thing. It's really just saying the same thing in three different ways here, because if you look at ax less than or equal to b, so the set of x's that satisfy that is a polyhedron, and it's also the solutions to a linear program, and then it's an intersection of half spaces because each of the rows of so I have a matrix A and a vector B and all these less than or equal to constraints, and so a row corresponds to a constraint, and so the x's have to satisfy that inequality. And satisfying the inequality corresponds to living on one side of the half space, living in one half space and not the other. And so then but you don't have to just satisfy this one constraint, you have to satisfy all the constraints. And so that's an intersection of constraints. And so that's why an intersection of half spaces is the same thing as those other two things, the polyhedron and the set of feasible solutions for the linear program. So therefore we can conclude that ax less than or equal to b defines an intersection of half spaces, and we get this, just this little picture here. So these things are all equivalent. That's what we've just shown. That feasible region of a linear program, in other words, that's a polyhedron. So in plural, a polyhedron is a poly. The plural of polyhedron is polyhedra. And anyways, okay, so we have those two things are equivalent, and then also it's equivalent to an intersection of half spaces. So these things are all the same thing. You can, of course, analyze polyhedra just as shapes in and of themselves from a geometric point of view without the context of a linear program. But for every polyhedron, you can figure out a linear program that realizes that polyhedron as its set of feasible solutions. The question is that linear program relevant to whatever you're doing or not? But, of course, from our point of view, we're starting with linear programs. So the context of linear programming is always there. But anyways, so that's what we have. So when you're thinking of the set of solutions to a linear program, you should be thinking of something like that purple set that we drew before, which is a polyhedron. And that is an intersection of half spaces. Okay, so that's it for this video, and we will continue with more geometry in the next videos. Thanks for watching.